In this video, I'm going to talk about one of the power electronic device, thyristors. So we have three types of power electronic devices. One is power diodes, another one is thyristors, third one is transistors. When it comes to the transistors, there are different types again, BJTs, MOSFET, IGBTs, etc. When it comes to thyristors, there are different types. We're going to talk about it. And diodes also, there are power diodes and fast recovery diodes and Schottky diodes. Those are the types we talked in the previous video. Now, thyristor. Thyristor acts like a controlled switch. So basically, I can tell the thyristor when to turn on and when to turn on. Okay, so that's the reason we call this a control switch. Can we say when to turn off? Not every thyristor. There are, I think, one or two we're going to discuss in this video down the line, but most of them we can control when to turn on. Okay, now a thyristor is a three-terminal device. So the three terminals are anode, cathode, and gate. So every thyristor, we're going to talk different types. So every thyristor has almost all the three terminals. Okay, that's the reason I ended up calling thyristor. It's a three-terminal device. So the thyristor working principle is when a small current passes through gate, so it is going to go to the gate to cathode. The thyristor acts like a closed switch as long as anode voltage is higher than cathode. So basically, as I mentioned, it's a three-terminal device. Okay, so I'm going to represent, basically this is an SCR, that's anode and cathode and gate. Okay, if I don't give any gate voltage, there is no current passing through anode to cathode. Okay, whenever I supply gate current, then it will act like a closed switch as long as this voltage is higher than this voltage. Okay, anode voltage is higher than cathode voltage, and when I supply small amount of current, that's called triggering. When I trigger the gate current, it will act like a closed switch. Once a thyristor is in conduction mode, so that means when it is closed switch, the gate current has no control and the thyristor continue to conduct. So as mentioned, so once I give a triggering signal, that trigger signal, there will be a continuous current passing from anode to cathode as long as anode voltage is higher than the cathode voltage. Okay, in that case, the gate current is no longer needed. So it will lose its control. Whenever the cathode voltage is higher than anode, then it will act like a open switch again. At that time, to trigger, or at that time to act like a closed switch, it needs the gate voltage. Okay, typically 0.5 to 2 volts is the voltage drop across the thyristor. Depending upon the thyristor type, the voltage drop changes from 0.5 to 2 volts. Now, thyristors allow current only one direction. Not every thyristor, there is a triac we're going to discuss in this video. A triac is exception. It allows current in both directions, but this here, SCR is one of the major thyristor. It allows current in only one direction. Now, we can turn off the thyristor by making cathode voltage higher than or equal to the anode voltage. As long as this value is higher or equal to anode, then it will act like an open switch. So there are different types of thyristors. Okay, forced commutator, line commutator, gate turn off, reverse conducting thyristor, static induction thyristor, gate assisted turn off thyristor, light activated silicon controlled rectifier, MOS turn off, emitter turn off, integrated gate commutated, MOS controlled. So out of these 11, all those 11 comes under these three categories. Okay, one is SCR, silicon controlled rectifier, Another one is GTO, which is gate turn off thyristor. Another one is MCT, mass controlled thyristor. Mass indicates that metal oxide semiconductor. Okay, metal oxide semiconductor controlled thyristor. Okay, so every thyristor comes under these three categories: SCR, GTO, and MCT. Now, I'm going to talk about SCR. I see many places they use SCR, a synonym of thyristor, because it's really cheap, okay, and easy construction. So that's the reason I think whenever you see thyristor, SCR is the synonym for thyristor. But there are different types of thyristor, and SCR is one of the thyristor, silicon controlled rectifier. It's a basically it's a 3-terminal device, but it is nothing but a PN 2 diodes connected together. Okay, now whenever I connect, and here is a symbol, okay, anode, cathode, and gate. Okay, now whenever I connect some voltage, say for example like this, okay, anode is connected to the higher voltage, cathode is connected to the lower voltage. So this is positive, right? That is negative. Here p-type material, so holes, those are positive, repel each other, and negative, even these electrons will repel each other. So what happens to this junction? This junction will be act like a forward biased, so act like a closed. This junction will be act like a closed. But the middle junction right there, this is going to be reverse biased. Okay, so why is that? Because I mean, all the holes are going to go towards this, all the electrons are going to go towards left, so this barrier is going to expand, so it will act like a open switch until we give the gate voltage. So whenever I give a signal to the gate, that signal is also called triggering. Okay, so whenever I trigger the gate, there will be this junction is going to be closed and the current is going to pass in this direction. So now it will act like a closed switch. Okay, now it will start conducting current as long as anode voltage is higher than the cathode voltage. Once I trigger, now it doesn't matter whether there is a voltage across the gate or not, it will continue supplying energy as long as anode voltage is above the cathode voltage. Now the VI characteristics are going to be like this. I mean, if you look at the diode is going to be something like this, almost same in the reverse biased, but in the forward biased it's a little bit different for the SCR. I'll tell you how and why. Okay, before going there, how and why, I want to talk about the terminology I used here. So here is the voltage, this is forward voltage and the reverse voltage. This is forward voltage, reverse voltage. This is the current passing through the SCR. VRB is the reverse breakdown voltage. So you don't want to apply higher than the VRB. If you apply higher than the VRB, you are permanently damaging your SCR. VFB is also forward breakdown voltage. That's also the voltage you don't want to cross. If you cross that voltage, you will permanently damage your SCR, silicon controlled rectifier. Now, so here, as long as you start applying the voltage, okay, it will not, unless I give the gate voltage, it will not trigger. Say if I apply the gate voltage right here, okay, now what does it mean when the voltage is right there? That's what I meant. Okay, when this is the voltage, right? X-axis represents the voltage. So 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt. I mean, I just gave you those numbers, but usually for the power electronic devices like SCR, it could be like 5000 volts. Okay, now So when I trigger the voltage or trigger the SCR right there, what happens, it will start conducting right there. So it's going to be, the characteristic is going to be, curve is going to be like that. Or if I give triggering at 4 volts, then it's going to be triggered like that. Now, so the important point, current can flow from anode to cathode all the time. So SCR will not conduct current in opposite direction. It's a unidirectional device, always goes from anode to cathode. Gate current is required to turn on the SCR. So to turn on the SCR, you need the gate current. Once the SCR is turned on, gate current is no longer required. So once it is turned on, gate current doesn't have any effect. Now, anode voltage must be higher than the cathode voltage to conduct electricity. Now here I'm using two terminologies. One is IL is somewhere there, IH. Okay, IL is called latching current, IH is called holding current. Now IL is latching current. Latching current is nothing but the minimum forward biased current from anode to cathode to turn on the SCR. Okay, so once I supply the gate signal, say that gate signal, the triggering voltage or triggering current needs to be certain time, like 5 microseconds, 10 microseconds, something like that. So instead of 10 microseconds, say I gave that signal only 0.5 microseconds. Okay, so in that case, it's not going to turn on, right? Because that 0.1 microseconds is not sufficient to close this gate or junction. Okay, so now, but if I give that 10 microseconds, then it will start conducting. So IL is called the latching current whenever that minimum current once the SCR is turned on. Now IH is the holding current. Holding current is a little less than the latching current, but they are pretty much close. Okay, holding current is a little less. So basically once you turn on, now it has to have minimum current to turn on or to keep the SCR on. So holding current is nothing but the minimum forward biased current to keep the SCR on once it is turned on. So to keep it on, you need to have the minimum current. That minimum current is called holding current. Okay, the next part is gate turn off thyristors. I'm going to stop this video here. I'll continue GTOs in the next video. Thank you.